We should now be pretty familiar with the reactivity series. We want to go back to it for a second because what we've said before is that we can make anything towards the left on the reactivity series by reacting it with something on the right with an appropriate nucleophile. Now this should make you a little bit uncomfortable because if acid chlorides are all the way to the right, we want to know how do we make them. And the answer is that we actually take the carboxylic acid and we turn the carboxylic acid into something we sort of jokingly call the superleaving group. Right? And so there are two primary ways of doing this. The first way is by the reaction with thionyl chloride. All right, so thionyl chloride is SOCl2. Okay, and so we're going to take the carboxylic acid and we're going to react it with thionyl chloride, and we're going to generate the acid chloride. Right, so we can't make the acid chloride from any other reagent in the reactivity series except for the carboxylic acid. So the first thing that happens here is that we get the oxygen lone pairs are going to attack the sulfur and displace a chloride anion. And so for that, we have a system that looks like this. The oxygen is still positively charged, but we have a oxygen sulfur bond now, which is new. The chloride is going to come along and it's going to do a deprotonation, and that's going to give us a neutral species. And this neutral species has what I like to call a superleaving group inside. All right, so this unit here is what I'm going to call the superleaving group. Right, or the SLG. And the reason we call it a superleaving group is because it has some small molecule embedded inside. Right, so we're under acidic conditions, and so what we can do is we can protonate the oxygen lone pairs. Right, so we've got superleaving group still attached. The chloride here can undergo a nucleophilic attack, and so chloride anion is going to attack the activated carbonyl. All right, and what that's going to generate is a new tetrahedral intermediate. Like this. And now again, we still have this superleaving group here. And so what happens at this point is that the lone pairs will come down to reform a pi bond, but because you have the superleaving group, you have an entropy gain, because what's going to happen is that you have a small molecule embedded within inside that molecule, and so you're going to generate a small molecule as one of your byproducts, and that small molecule happens to be SO2 gas. Okay, and so we also have a chloride anion. The chloride anion is going to then deprotonate the protonated acid chloride to give us the acid chloride product. And so the net result is that upon collapse of that tetrahedral intermediate, the superleaving group leaves and it will form SO2 gas, and there's, of course, entropy gained here. And so once that SO2 bubbles away, it's not coming back, and the reaction is going to go to completion. All right, so this is one way of making acid chlorides from carboxylic acids. There is, of course, another way of making acid chlorides from carboxylic acids, and that's the reaction with case of the thionyl chloride here. We can sort of put those onto the reactivity allyl chloride. And this reaction is actually very similar to the reaction with thionyl chloride in the sense that we're going to use or take advantage of the fact that we have a superleaving group in our molecule. All right, so the reaction with oxalochloride is COCl2. All right, so we're going to take the carboxylic acid and we're going to react it with oxalochloride. So oxalochloride looks like this. And normally we do this reaction in the presence of triethylamine as base, and of course we get the acid chloride. Okay, so we know that anytime you have base in the presence of a carboxylic acid, you're going to undergo a deprotonation, and so that's going to generate the carboxylate. It's this carboxylate that then reacts with oxalochloride. Oxalochloride is a highly, highly reactive molecule. You have to be very careful with this. And so it's going to attack and give us a tetrahedral intermediate. Like this. We're going to collapse that tetrahedral intermediate with loss of chloride anion. Okay. Now at this point, this is where the superleaving group is, because you've got two molecules that are small molecule gases. One is the CO2 and the other is the CO. Because what can happen next is the chloride anion that left just before can come back in and attack the carbonyl carbon, forming a tetrahedral intermediate. This tetrahedral intermediate then collapses with loss of the superleaving group. But this time the superleaving group is going to liberate CO2, a molecule of CO, and a molecule of chloride anion. And so CO2 gas bubbles away, CO gas bubbles away, and then you've got chloride anion as a byproduct, and of course you can get the product acid chloride out of that set of arrows. So again, entropy is gained in this reaction. The reaction is pushed towards completion because you have two gases that are going to shift the equilibrium towards the products. And so these intermediates in which you've got the superleaving group kind of embedded and sort of responsible for a nucleophilic attack right here, so why don't we just update the reactivity series now. We of course have the carboxylate, we have the amide, we have the ester, we have the carboxylic acid, which is about the same as the ester. Then we have the ketone, then the aldehyde. Aldehydes are more electrophilic than ketones. And then we have the acid anhydride. Then we have the acid chloride. But then I'm going to put a dotted line to indicate that what comes next is not isoluble, meaning we can't actually physically isolate it. And so this is the one in which we have the superleaving group, the SLG. Right? So this one is not isoluble. You cannot isolate those species, but what you can do is you can take the carboxylic acid and make the superleaving group substitution. And you can do that with either thionyl chloride or oxalochloride. From there, you can treat that molecule in situ with chloride, and that can generate the acid chloride. And so again, we're trying to make something to the left on the periodic table, on the reactivity series, from something on the right. And so what we do is we convert the carboxylic acid into something that is more electrophilic than the acid chloride is, and we can treat that thing with chloride anion to give us the acid chloride. And so again, we can treat this with chloride anion, and that's how we get the acid chloride. All right, so we want to shift gears a little bit and talk about another set of reactions, and these involve carboxylic acids, but these are known as coupling reagents. So remember that when we tried to take a carboxylic acid in the presence of a primary amine, and we wanted to form an amide bond, we said that this reaction doesn't happen, right? So we said that this reaction doesn't occur because what immediately happens instead of forming the amide bond is that any base, in this case the lone pairs on nitrogen, will make the carboxylic acid the carboxylate plus the ammonium ion, and now both species are completely dead. Okay? And so we can't take carboxylic acids and amines and react them together to make amides. This reaction doesn't work. Right? And so the amine simply protonates, become the ammonium salt, which is not nucleophilic, and the carboxylate becomes negatively charged, that's very electron rich, and so it's not electrophilic. Now we could convert the carboxylic acid into an acid chloride, but larger, more complicated structures might not behave well under the thionyl chloride or oxalochloride conditions. So in order to directly promote the formation of an amide from a carboxylic acid and an amine, most of these are commercially available. We can actually use a coupling reagent, or sometimes known as an activating agent. And this activating agent essentially converts the carboxylic acid into an intermediate that has sort of super leaving group-like reactivity. All right, so let's talk about that now. And so let's take a carboxylic acid. Let's take this one, and let's react it with an amine. But this time we're going to react it in the presence of DCC. DCC stands for dicyclohexyl carbodiimide. In the presence of DCC, what we can do is we can actually generate that amide. Okay, now how does this work? We react it with DCC. The carboxylic acid reacts with DCC. Now DCC looks like this. It has a carbon-nitrogen double bond, carbon-nitrogen double bond. So that central carbon atom is sp hybridized, and it has two cyclohexyl rings coming off of the nitrogen. So what happens first is the nitrogen lone pairs, because they're basic, are going to actually deprotonate the carboxylic acid. So we're going to form a carboxylate, right, plus a protonated form of the carbodiimide. And at this point, what can happen is you can get the carboxylate lone pairs attack that central carbon atom, which is really, really electrophilic. Okay? And so when you do that, what you're going to generate is a new carbon-oxygen bond. Okay, so we've got now an H here appended to the cyclohexyl ring, doubly bonded to the nitrogen, which now has the other cyclohexyl ring. Now, at this point, it's almost as if this whole thing right here is the super leaving group. And so this has similar reactivity to what we had before, in which now we can take an incoming nucleophile, this time the amine. Now the amine can attack the carbonyl carbon to form a tetrahedral intermediate. Okay, so we generate a species that looks like this. Okay, and we get a proton transfer event happening. When that proton transfer event happens, we get a neutral species. Right, we still have our activated system. Right, so we still have that sort of super leaving group-like reactivity. What can now happen is the lone pairs on oxygen can come down and form a new carbon-oxygen bond. This time, you can get the carbon-oxygen bond of the superleaving group to leave, and it's going to form a deprotonated urea. Okay, so what do we have here? We've got the protonated amide. All right, plus we've got the deprotonated urea. And this deprotonated urea can come in and remove the proton onto the amide, giving you the product structure. Right? The other byproduct of this, of course, is going to be the urea. And you can think of the urea as being a very stable molecule, right? Because it's got sort of two amide bonds. Right? So this is incredibly stable, and it's like a super leaving group that's not going to come back in and point the reaction in the reverse direction. And so you can sort of see how this type of coupling reagent resembles the superleaving group-like reactivity that we had for oxalochloride and thionyl chloride. All right, so that's the formation of an amide. Coupling agents or activating agents are also useful in the synthesis of esters, especially those that are macrocyclic lactones. So remember, lactones were those cyclic esters. So let's consider the following esterification reaction. Let's say we start with this carboxylic acid. It has, various decorations on it. But what really matters here is that we want to form a bond between the oxygen and the carbonyl. We want to form a lactone. So we take this molecule and we treat it in the presence of another type of coupling reagent, EDCI. So EDCI has the following structure. Right? So it's very similar to DCC, with the exception that it's got a different tail on either side. Now, in the presence of EDCI, what we can generate is a cyclic ether. And so the cyclic ester. So the molecule looks like this. Okay, and so we're forming this this lactone. A macrocycle is just one in which we've got more than 6 atoms in it. So it's a macrocyclic lactone, meaning it's a large cyclic ester. And so this reaction works really well. It works in 78% yield. And so how does it work? Well, remember that the first thing that happens in this reaction is you get activation of the coupling reagent and formation of the cyclic ester, formation of the carboxylate, excuse me. And so I'm just going to abbreviate the rest of this structure by drawing something that looks like this. Right, and so that's just a generic way of saying that we're really focused on the two functional groups that we really need in this reaction. And of course, we've got the activated coupling reagent. Okay, so at this point, we take the carboxylate. We're going to attack the coupling agent. And that's going to give us an intermediate that looks like this. Okay, and now I've got this alcohol intramolecularly can attack the carbonyl carbon. And so when I do that, what do I generate? I generate an intermediate that looks like this. So I'm going to say this alcohol is going to attack the carbonyl carbon. To give me an intermediate that looks like this. Okay. This then collapses with loss of the leaving group. The leaving group this time is a, first thing that happens is we're going to lose a proton because this is protonated, right, to generate a neutral species. Okay, so we have something that looks like this. Okay, and then we get collapse with loss of the super leaving group this time. And the super leaving group, of course, is the urea. And the urea can do the deprotonation of that protonated cyclic lactone to give you the full macrocycle, and I've written it out here. The byproduct of this reaction, of course, is the urea, and the urea is a very stable molecule. It looks like this. Okay, so these coupling reagents are important in synthesis because they allow us to overcome the limitation of taking carboxylic acids and amines and forming amide bonds directly. We can't do that normally unless we add these coupling reagents in which the carboxylic acid is going to be temporarily converted into something that has a super leaving group like reactivity, like this embedded urea right here. Okay?